This is slide number 22 and I am your presenter Asloob Mudassar. Here we talk about generalized Fourier transform. That is the integrals, that is the Fourier integrals do not obey the definition of integration, but still the Fourier transform exists. Such Fourier transform are called generalized Fourier transform. So let's read the statement. Due to infinite discontinuity at the center of object O1, the Fourier transform of such an ideal point source should not exist, but in reality that does exist. The Fourier transform of such objects are called generalized Fourier transform. Let's compute the generalized Fourier transform of the object O1. So we have O1 left hand side, the capital O1 which with variables with the Fourier variables fx and fy, that is equal to the Fourier operator operating on O1, and on the right hand side we have the double integrals both from minus infinity to infinity, and we have the object O1, and you know that these are the factors which appear, that is e to the power minus iota 2 pi within the bracket fx into x plus fy into y. This factor appears in the definition of the Fourier transform. So we have just plugged in the value of O1 over here. And you know that O1 is actually delta of xy. So we have placed the value of delta xy of in this integral. And if you evaluate this integral, then you know that this integral will be equal to 1 by definition of the delta function. Because in order for the delta function to be non-zero, x should be equal to 0, y should be equal to 0. And when we put these, when we put the values of x is equal to y is equal to 0, it means that whenever you put the values, whenever you assign some values to x and y variables, then of course the integration will vanish out, and if you put these values in the exponential factors, that is x is equal to 0, fx into 0 plus fy into 0, then you know that in the exponential function we have e to the power 0 which is equal to 1. So we have written 1 over here. And now let's compute the generalized Fourier transform of the function O2. The function O2 was a plane wave. And you know that on the right hand side we have, on the left hand side we have written O2, capital O2 as a function of fx and fy, means that we are talking about the Fourier transform with the Fourier variables fx and fy. And then we have the operator operating on O2, and on the right hand side we have the double integrals where we have plugged in O2. And O2, you know that is a plane wave of infinite extent. So we have put the value of O2 which is equal to 1 in the integral. And this integral is separable in x and y coordinates, so we have separated them into two integrals, one over the x variables and the other on the y variables. So the x variable integrals, you know that will give you delta of x, because again when you put x is equal to 0, then of course the integral will vanish out because we are assigning the value x is equal to 0, and e to the power 0 will be equal to will give you e to the power, of course that one will give you delta of x, and similarly the other integral will give you delta of y. If you combine these two integrals together, these two delta functions together, you will get one Dirac delta function which is delta of x and y, which is a two-dimensional Dirac delta function. And you know that this represents a point source. So it means that if you take the Fourier transform of a plane wave, then you will get a point source at the location x is equal to 0, y is equal to 0. Now let's compute the generalized Fourier transform of the function O3. O3 was you know that was a cosine function which is equal to 1 plus cos of 2 pi fx into x. And on the left hand side we have represented the Fourier transform by O3 with the Fourier variables fx, fy, and the operator is operating on small o3 with the variables x and y. So the same operator is operating on the cosine function 1 plus cos of 2 pi fx into fx. In the second row we have o3 and the Fourier operator is shown, but here we have represented cos in terms of its exponential format, that is half e to the power iota 2 pi fx x plus half e to the power minus iota 2 pi f into x. So this is the representation of the cosine functions. Now let's compute. So these will actually three integrals. One integral will be over 1, the other integral will be on the second exponential, the third integral will be on the third exponential function. So we have these three functions which we have shown over there, three integrals. So we have written O3, then we have written the value of O3, which is split into three forms: one, the other exponential, the second exponential, and then the third exponential. So these three integrals will operate on these one, and then of course from the first integral, you know that the first integral is 1, and 1 mean plane wave, and we have evaluated that the Fourier transform of that integral is a delta function point source. So we have written that the first integral solved as a delta of fx comma fy. Now the other two integrals we can write them as we can split those integrals into x variables and y variables. So we have written them as two integrals, one over the x variables, the other over the y variables. So we have splitted the second and third integrals into x variables and y variables. And you know that if we evaluate these integrals as we have evaluated the previous integrals, the first integral will give you delta of fx comma fy, the second integral will give you delta of fx minus f comma fy, the third integral will give you delta of fx plus f comma fy. So you see that in all these integrals the fy have a constant the contribution from the fy integrals is the delta of fy, which we have combined in a two-dimensional form. So we have written the second integral as a delta of fx minus f comma fy, and we have combined the third integral also into two-dimensional delta functions as a delta of fx plus fy comma fy. So since we have dropped the factors, half factors over here, so this half factor and this half factor we have dropped in the calculation of the Fourier transform, and then we are plugging them back. So the original Fourier transform will be the original Fourier transform of the object O3 will be equal to capital O3 in the Fourier variables fx and y is equal to delta of fx comma fy plus the contributions from the two integrals with exponentials of the cosine functions. One is half into delta of fx minus f comma fy plus half into delta of fx plus f comma fy. So you see that we have computed the three generalized Fourier transform. We have calculated the Fourier transform of O1, generalized Fourier transform O1. Then we have computed the generalized Fourier transform of the function O2. Then we have computed the generalized Fourier transform of the function O3. And here this ends with the Fourier. So here we end the Fourier slide number 22.